Okay, and Hannah will be telling us about her work with Dr. Crawford, characterizing this interesting I'm not going to be able to say it, capsaicinoid. Yep, capsaicin is a version I know, but in chili peppers and other pepper products.
All right, so thank you for the lovely introduction, Dr. Waters. As she said, my name is Hannah Cole, and today I'm going to be talking about the characterization of capsaicinoids, their content in chili pepper fruits and pepper products. This is going to be a methods comparison as well as looking at some of their practical uses. And my advisor for this was, again, Dr. Crawford. All right, so just a small overview of what I'm going to be talking about today. I'm going to start out with an introduction. We're going to look over some of the history of pepper research, as well as some of the chemical properties of capsaicinoids that you need to know for this talk. And then I'm going to move into a discussion. We're going to talk about the biosynthetic production in plants, the mechanisms of action within the human body, some of the characterization methods that have been done on capsaicinoids, as well as my research here at UW-Oshkosh. And then to end off, I'm going to talk about some of the potential for future research. All right, so first I'm going to start by talking about the history of pepper research. For over 6,000 years, it has been known that peppers have been used for culinary purposes as well as a preservative. We think that this is due to the antifungal properties and the oleoresin of the capsicum species. And dating all the way back to 5000 BC in the Tehuacan Valley in Mexico, it is seen that Mayans as well as Aztec civilizations did use peppers. And the word chili does actually come from the Nahuatl language, which was spoke by the Aztecs. But it wasn't until 1492 that this was introduced into Europe. And this was done by the discovery of Christopher Columbus. And black peppercorns, interesting enough, were used as currency, and they were referred to as black gold. All right, so we're going to look at some of the classifications for peppers. They are part of the Solanaceae family, the capsicum genus, and there's a small discussion about the species. In the 1680s, there was an English doctor by the name of Robert Morrison who actually believed that there were up to 33 different types of species. Today we know that there's probably less, but it is still argued that there are around 25 species. However, we do know that there are 5 domesticated, and those are the frutescens, the annum, the chinase, pubescens, and bacatum. Looking back at the family, just a fun fact, peppers are kind of the cousins to tomatoes, potatoes, cowpeas, and even tobacco plants and eggplants, so kind of a fun fact there. It wasn't until 1816 when scientific experiments actually began on peppers, and Christian Frederick Buchholz was actually the first scientist to conduct pepper research, and he even coined the term capsaicin. Structures weren't even determined until 1919, and this was by E.K. Nelson, but this came after a long road of research conducted by John Clareau Thresh as well as Carl Miko. And this was the structure that was determined. This is our capsaicin structure, which we will look at more later. In 1910, this was 9 years before we even knew what the structure of capsaicin was, one scientist was actually gaining momentum in the field of quantifying spice from chili peppers. His name was Wilbur Scoville, and he followed the Scoville organoleptic test. We also know this as the Scoville heat unit scale. This scale measures the psychological effects in response to contact of pepper on the human tongue. His method included capsaicin extractions with alcohol, and these were then diluted into sugar solutions. These dilutions do correspond to the relative spiciness of the pepper, and this is then a method using human taste test. There are 5 classes, very creatively named. We have non-pungent, mildly pungent, moderately pungent, highly pungent, and very highly pungent. So I do have a question for you. How are we going to convert these into something that we quantify as ppm? All right, so in the 1960s, we started learning more about the constitution and biosynthesis of capsaicin. And in 1961, Japanese chemist S. Kosugi and Y. Inagaki discovered a group of chemicals in the fruits that contributed to the spiciness. And these are what are known as the capsaicinoids. Further research led to a better understanding of how capsaicinoids were produced within the fruits themselves. We know that some of the chemicals involved in these pathways are phenylalanine, cinnamic, p-coumaric, caffeic, ferulic acids, and 2 that I want you to pay special attention to that I'll talk about more are vanillin and vanillamide, or vanilamine. these were actually discovered using radio tracer studies. In 2010, studies started showing that the heat was actually produced in the vesicles or vacuole-like subcellular organelles within the epidermal cells of the placental tissue in the chili pepper fruits. That's a lot to take in, so I have this lovely picture for you. Here is our inocular septum, and our placental tissue is right in here. Here's a close-up of this, and as you can see here, there's these small blisters, and within these blisters is where the capsaicinoids are actually produced. Something to note there, a lot of people think that capsaicinoids are related to the seeds within the pepper. They are actually not produced or have anything to do with the seeds, but the seeds actually absorb them, and that's why we think that the seeds are the spiciest part of the pepper, but it's actually these blisters where they are produced. All right, next I'm going to talk about some of the chemical properties you need to know for this presentation. Capsaicin is the most abundant and naturally occurring alkaloid which is found in the chili pepper fruits. It is semi-volatile, colorless, odorless, and a hydrophobic white crystalline powder. And it is also fat, alcohol, and oil soluble. This fact right here is actually why they tell you to have a glass of milk after you eat something spicy due to its ability to be fat soluble. Something else you could do is have a nice cold beer if you're of age, or you can have a teaspoon of olive oil. I think that'd be gross, but that's your preference. Dihydrocapsaicin is the second most predominant capsaicinoid. It does not contain the double bond in that capsaicin displays. And what I mean by that is this double bond right here, but we'll look more about the variations of the different structures of capsaicinoids later. Looking more specifically at capsaicin, it does consist of an aromatic vanillyl ring, and I had mentioned before that E.K. Nelson had performed radio tracer studies in order to determine the structure, and what I mean by that is there was a radioactive C11 carbon being attached right here, which helped them determine that there was a vanillyl ring on the capsaicin. Next, there also consists an aliphatic hydrophobic fatty acid tail. All right, so there are over 20 known plant-produced capsaicinoids. But for this talk, I'm going to be focusing on capsaicin and dihydrocapsaicin. And the reason for that is they actually make up 77 to 98% of the major capsaicinoids, or making them the major capsaicinoids. As mentioned before, there's an observable difference in the double bonds, and this accounts for the saturation of the tails. There's a vanillin moiety with a varying ACL chain on all of these. Notice that some of these are vanillylamine moieties, and some of them actually only have oxygen groups attached, and they all vary in the length of their fatty acid chains. And again, not all contain amide groups. All right, so moving into my discussion, I'm going to first talk about the biosynthetic production within the plants themselves. In 1919, it was assumed that the structure of, or the formula of capsaicin was C9H14O2. But as mentioned before, there are amine groups that are present, so this neglects for the nitrogen presence altogether. The next assumed formula was C18H28NO3, and this was based on the analysis of the molecular weight determinations. However, this is an impossible formula. Now what I mean by that is this actually doesn't follow the nitrogen rule, stating that if you have an odd number of nitrogens, you should have an odd number of hydrogens. Therefore, the proposed formula by E.K. Nelson, which we know today, is C18H27NO3. All right, so E.K. Nelson actually determined the structure based on this method. It involved preparing a benzoyl derivative and melting at 74 degrees, taking an alcohol solution and treating it with planktanic chloride and hydrochloric acid, which would cleave the molecule, and this allowed for the solution to evaporate spontaneously. Now, I had mentioned before to remember those vanillin and vanillamine chemicals that are involved in the biosynthetic production, and during this step, when it did evaporate spontaneously, there was a vanilla-like odor, and this is what led to the discovery of there being a vanillin residue within the capsaicin structure. All right, it wasn't until the 1980s before scientists began understanding how they were produced within the fruits, and the first pathway for the biosynthesis of capsaicinoids was determined at this time, but it wasn't until recent, in the early 2000s, when they discovered that there is actually a second pathway involved in this synthesis. So today we now know that the two pathways that converge include the phenylpropanoid pathway and the branched chain fatty acid pathways. And these provide the precursors phenylalanine and valine or leucine respectively. All right, so here we have our two main structures that come together, our vanillamine and our 8-methyl-6-nanoyl-CoA, and they come together in a capsaicin synthase to create our capsaicin structure. Now, as much as I'd like it to be that simple, the full pathways are actually much more complex. This is what they look like. This is a lot to take in, so for the purpose of this talk, I am actually going to break this into two. And then I'm first going to talk about the phenylpropanoid pathway on this side, and then I'm going to talk about the fatty acid synthesis on this side. All right, so starting off with the phenylpropanoid pathway, we first take our phenylalanine precursor, and we're going to do a phenylalanine ammonia ligase, getting rid of this ammonia group, and that ends us with cinnamate. From there, we're going to perform a cinnamate 4-hydroxylase, which will actually put on, or hydroxylase, which will put on the hydroxyl group right here, giving us coumarate. And then we do a 4-coumaryl-CoA ligase, which will then put on this CoA ligand right here. Next, we're going to take our 4-coumaryl-CoA, and we're going to put it down this path right here, which first starts with the hydroxycinnamoyl transferase. There is the option to go this way, which would involve a p-coumaryl-shikimate quinate 3-hydroxylate transferase. But for the purpose of this, we're going to focus just on this path right here. From there, we get our caffeoyl-CoA, which experiences a caffeoyl-CoA 3-O-methyltransferase to get our ferroyl-CoA. And from there, we then do our hydroxycinnamoyl-CoA hydratase ligase, giving vanillin. And then aminotransferase brings us to our final compound, the vanillylamine. All right, next, the fatty chain pathway. This starts off with our valine, putting it through a branched chain amino acid transferase, giving this structure here, and then that goes through an isovalerate dehydrogenase, giving our isobutyryl-CoA. From there, it gets pretty tricky, and it does actually go through the 3-malonyl ring 3 times, and within there, it experiences a ketoacyl ACP synthase and acyl carrier protein lyase as well. This process right here actually is what determines the fatty acid length on the different capsaicinoids. So from here, for capsaicin specifically, we do end up with 8-methyl-6-nonanoic acid from a fatty acid acyl-ACP thioesterase that happens here. And then finally, if we put it through an acyl-CoA synthase, which lengthens the C2 chain with acyl-S-CoA, we end up with 8-methyl-6-nononyl-CoA, which is our second structure that is involved in the capsaicin synthase. All right, so this is actually where the variation in the capsaicinoids occur, and again, that is referring back to that ring of determining the length of the fatty acid chains. All right, so next I'm going to talk about the mechanisms of action that happen in the human body when we eat these hot peppers. Inside the mouth, including areas of the tongue, there reside neurons which carry, that relay non-inceptive or tissue-damaging information to the brain. These neurons are part of the transient receptor vanilloid, potential vanilloid family, or otherwise known as the TRPV family. Of these, TRPV1 is the most extensively studied, and one of the reasons for this is because capsaicin is the agonist for this pathway. The TRPV1 channel, otherwise known as the capsaicin receptor or the vanilloid receptor 1, functions to detect and regulate the body's temperature. This is part of the, one of the roles of TRPV1 is actually sensing scalding heat and pain, which is why we experience that sensation. And just a small fun fact here, birds actually don't have TRPV1 receptors, and we have our Senegal parrot here, and he's actually eating our red hot chili pepper, unfazed by it. And this actually sparked the idea for using capsaicin in gardens or even bird feeders. So if you go home and have squirrels in your bird feeders, put some hot peppers in your bird seed. All right, so next I'm going to look at the sodium ion gated channels and how they work. TRPV1 activation is a little unique in the sense that it is actually a dual gated model. As you can see here, there are two gates. This is our selectivity filter, and this is our second inner gate. And just kind of defining some of our substances here, we have our RTX capsaicin, which is resveratroltoxin coupled with capsaicin. And just for the sake of fun, I have DKTX attached with a proton, and DKTX is a vanilla toxin, which is found in the toxis of the Psalmopoeus cambridgei, which is the tarantula spider. All right, so what we're going to have happen first is this, wrong button. The capsaicin is going to come in, and it's going to bind in this outer hydrophobic pocket. And as that happens, that's going to encourage the opening of the bottom gate. As that happens, you can notice that there's actually no change in the selectivity filter up top, and that is until the opening of the lower gate happens. As this happens, there is actually a higher affinity for the opposite gate to open as well. Something to be noted, if this spider toxin was not here, this upper gate would open without it. So just to clarify, you don't have to have both in order to open both gates. And as you can see here, the spider toxin does attack at the selectivity filter, and then it opens the top, opening the bottom as well. So if you were eating hot peppers and got bit by a tarantula, you'd be in for a world of pain. All right, so as mentioned before, as these gates open, it does open to a voltage-gated sodium ion channel. All right, so next I want to talk about the characterization methods of capsaicinoids that have been experimented with. All right, so in 1910, Wilbur Scoville was inspired by E.K. Nelson's claim that capsaicin is so hot that one drop of a solution, 1 in a million, or less than 1/millionth of a grain, will make itself known to the tongue. And since peppers are used in commercial markets and medicinally, it was pretty troublesome for farmers to actually produce peppers of the same level of spiciness. So that is one of the reasons why he ended up starting this test as well. And Scoville did believe that the human body was more efficient than any analytical instrument at this time due to the human body's vast array of senses. Therefore, he developed a test tasting method. His method was in fact able to perform testing levels that detected less than 1/millionth of a grain. And I keep saying grain, and for the purpose of this presentation, 1 grain is equivalent to 64.79891 milligrams. All right, so his method consisted of macerating 1 grain of ground capsaicin into 100 cc's of alcohol and letting it sit overnight. After shaking and filtering this solution, the alcohol was added to sweetened water in definite proportions. And this was done until a week, but very distinct spiciness was detected on the human tongue. In his study, he studied the Japanese chilies, Zanzibar chilies, and the Mombasa chilies, and they came out to a dilution factor as follows. All right, so this actually sparked what we know today as the Scoville heat unit scale. And if you ever see a pepper at the grocery store or anything that's being experimented with that you've heard of, it will most likely have a Scoville heat unit rating. But this doesn't apply just to peppers. It will also be for pepper products as well, such as USDA grade pepper spray. Also, there are chemicals such as the capsaicinoids themselves and other chemicals that have heat-like sensations that act on that TRPV1 receptor, such as resveratroltoxin. So we have our capsaicin and our dihydrocapsaicin there, and we have our resveratroltoxin here, which is actually an analogous chemical and that naturally occurs in a cactus-like plant in Morocco. And as you can see, pure capsaicin is 16 million, but resveratroltoxin is 1,000 times hotter at 16 billion. So that would be very painful if you got stung by that cactus. All right, so there are some problems with this test. Since it is a human-based test, you have to account for the variation between the individuals and their ability to taste, as well as the factors of having these taste tests over time. Continuously burning your tongue with these heat is not going to affect your ability to sense that spiciness. So also another thing to consider is due to the excessive amount of dilutions that he had to perform, it is incredibly time consuming. Due to the fact that this was also performed on wet samples, it does create a variation in with the results, which you can see on some of these, there are very, very wide margins of results. So, question for you, how do we make this better? Some of the methods that have been experimented with include thin layer chromatography, gas chromatography, and liquid chromatography. And some of the most notable detection methods include mass spectroscopy, UV-vis spectroscopy. All right, so I'm going to start by talking about thin layer chromatography. TLC is a successful method when analyzing the presence of capsaicin in hot peppers. Some of the most common mobile phases used for TLC experiments include toluene and chloroform. And for this talk, I'm going to focus just on one experiment that I had looked into. All right, so this particular paper actually studied a few different ways of developing TLC plates. They had various mobile phases, various stationary phases, and here are the samples that they analyzed. Something to note, the green hot pepper was actually done in 3 different concentrations. All right, so this method included preparing 10 grams of pepper. Then the extractions were performed using chloroform, and then it was extracted by soxhlet for 4 hours. They also used rotary evaporation, and then they took that volume of 5 mils, and they filled flasks up to 10 mils, which was followed by the addition of chloroform. The results on the next page are going to be for a silica gel 60 plate, which is spotted with 3 paprika and red pepper samples, as well as the 3 varying concentrations of the green pepper samples. The plates were then developed in the unsaturated normal chromatography chamber. Visualization of the plates was, in order to get visualization of the plates, they were sprayed with an alcohol solution and then exposed to iodide vapor. For analysis, this is where it gets pretty tricky with TLC. It does need to be coupled with a different instrument. So for this specific paper, what they did is they took the capsaicin they took the samples with the similar RF values as capsaicin, and they cropped them from the plates and then analyzed it using GCMS. So here are their plates from this paper. Focusing on this one specifically, we have A through F labeled at the bottom with these corresponding pepper samples. Excuse me. And we also have plates or standards 1 through 4 going up and down as well here. All right, so there are some benefits of using TLC. It is effective at detecting the presence of capsaicin, but there are also lengthy preparation procedures. It has use of dangerous and expensive chemicals, and it is unable to quantify the capsaicin content without coupling with another instrument. It is only good at qualifying the amount of capsaicin. It also does require difficult extraction from TLC plates if you are planning on quantifying your capsaicin using this method. So looking at something a little bit better, this would be gas chromatography. This way, by using gas chromatography, you can also quantify the amount of capsaicin. By using different methods of extraction, this can also be a very powerful tool. And if I'm actually going to focus on one paper from the Division of Agricultural Chemicals at the Indian Agricultural Research Institute in New Delhi, India. All right, so for this method, standards were prepared weighing out 50 milligrams of capsaicin and dihydrocapsaicin into acetonitrile at the following concentrations. And then they were freeze-dried before extraction, and ultrasonication was also used. And then they were centrifuged and filtered using nylon syringe filters. Characterization was done using GC coupled to mass spec. Here are some of the parameters that they used for their machine. Something to note is they did use a column temperature running up around 290 degrees Celsius. All right, so here is the results. As you can see, there's good separation, and we have our two peaks of capsaicin and dihydrocapsaicin here being the most predominant peaks, which is what would be expected. All right, so let's look at some of the benefits of using GCMS. This does allow for the detection of a whole range of capsaicinoids as well as other plant-specific compounds. It does ensure high reproducibility, and there are simple extraction procedures that can be coupled with this as well. But there's always room for improvement. Since GC is using higher temperatures, there is a potential for thermal decomposition within the inlet. So next I'm going to look at high-performance liquid chromatography. This is one of the most effective methods in quantifying capsaicin in peppers. It can detect capsaicinoids and capsaicinoids and more than other methods. There are actually claimed that there are 12 more than GC alone, and this is due to the stability of the molecules being analyzed. I'm going to focus on one method, which uses HPLC UV with a photodiode array detector to analyze capsaicinoids in their samples for this presentation. All right, so this method, a couple things to note. They did use an ethanol solvent as well as, they swirled it manually every hour, and they then extracted the supernatant of these samples and put them into HPLC vials for analysis. They also used standards which were prepared using serial dilutions to prepare a calibration curve. All right, these are some of the parameters for this machine. All right, so these are the results from this paper. As you can see, there's good separation of the capsaicin, the dihydrocapsaicin, and the nor-dihydrocapsaicin. So let's talk about some of the benefits. The identification and determination of most of the major and minor capsaicinoids can be reproduced with this method. Easy preparation makes for faster analysis of the samples, and they do remain in the liquid phase, which increases stability of the compounds being analyzed. So there's high reproducibility, and in comparison with the TLC method, the pumps make this analysis much quicker than having to wait for capillary action. But again, there's always a disadvantage, and the disadvantage for HPLC would be the cost of using the organic solvents. All right, so I'm going to talk a little bit about the extraction of capsaicinoids and some of the methods used for that. This is the most time-consuming process, so it's always careful to determine what method you want to do. The one that I'm going to be focusing mostly on is this salt-induced phase separation, which is the method that I chose to use for my research. These techniques are also in response to increasing market demands for faster and more efficient analysis. What I mean by markets is there's actually a few different markets that you can target with this kind of research. First, you have your consumers, so that would be your grocery store, all of you buying peppers. And then you've got your hobby novelty growers, such as New Mexico State Pepper Institute. And then you also have your salsa and salsa producers. And two to note would be Cholula and Frank's. And along with these markets, they're going to have various demands. So overcoming some of these market serviceability issues would include automated extraction procedures, shortened extraction times, reduced consumption of solvents, and minimized exposure to the personnel performing these experiments. All right, so now I'm going to talk a little bit about my research. All right, so what was the goal of my research? Efficiently quantifying the amount of capsaicin in chili peppers and pepper products. All right, so by doing this, we would have the ability to report the exact amount of capsaicin and dihydrocapsaicin in a vast array of pepper products. So who is this benefiting? Again, some of the markets would be hobby growers trying to grow the next record-breaking spicy pepper. Right now, the world's hottest pepper is the Carolina Reaper, And you can note that the Scoville heat units are between 855,000 and 1,041,427 Scoville heat units. Another market would be the producers and researchers of these novelty seeds, peppers, and products, such as the Chili Pepper Institute at New Mexico State University, and the sauce and salsa producers. For my research, I did focus on using Cholula hot sauce and Frank's Red Hot hot sauce. So those are pictured here. All right, so before starting my research, there were some variables that I needed to take into account. First of all, if we're trying to make a method for quantifying capsaicin, we should start with something that is already quantified. Makes sense, right? Next, for the presentation of the results of chili pepper plants, I will not be discussing some of the pepper samples that I did, and I'm only going to be focusing on one sauce, being the Frank's Red Hot hot sauce. The decision for choosing hot sauce is actually based on the quality guarantee and quantity guarantee that each of these sauce producers should be following as they're releasing their products to the grocery stores. All right, so next I had to choose a method of detection. There are many different methods of detection which show popularity, especially with capsaicin research. Two that I've already discussed in this presentation, if you noticed, would be UV vis detection as well as mass spectroscopy. But for this method, I did couple with mass spectroscopy. And this is due to the powerful abilities of mass spec. Mass spectroscopy has the ability to identify very specific compounds, and this is based on their mass to charge ratio. This method of detection has the type of specificity which is needed to decipher between all of the various capsaicinoids which are present in the chili pepper samples. So why not UV vis? This is due to coelution that occurs either between internal standards and your samples, or even with other chemicals that are in the plants and your sample or your chemical being analyzed. All right, so next, choosing a method of extraction. For my research, I chose using a salt-induced phase separation, or salting out, as my method of extraction. And one of the reasons for this is in order to be able to drive the capsaicin into the organic solvent that will be used. This method includes taking 5 grams of Red Hot hot sauce after being homogenized and weighing it into centrifuge tubes. Then 10 mils of acetonitrile was added along with 5 grams of our salt and our internal standard solution. The samplers were then shaken vigorously by hand every 15 minutes for 1 hour, and 1 ml of the supernatant was then filtered into HPLC vials using a filter tip syringe. My method started by preparing standards in the following concentrations, and 50 milligrams of a selected internal standard, being N-vanillyl 9 was added and was diluted into a 5,000 ppm stock solution and then into a 50 ppm stock solution. And 50 microliters of it was added to 1 ml of each of the combined standards. The data was then prepared using area ratios of capsaicin over the internal standard and dihydrocapsaicin over the internal standard as the dependent variable and the concentrations as the independent variable to prepare our standards graphs. So here are some of the parameters of my machine. A couple things to note. I did use a flow rate of 1.5 mils per minute, an injection time every 17 minutes, and we also used electrospray ionization. The equipment pictured here is from Thermal Electro Corporation, and the calculations were performed using Excalibur software. All right, so we're going to take a look at the standards chromatographs that were prepared. This particular chromatograph is a selected ion chromatograph for the 4 ppm capsaicin and 0.8 ppm dihydrocapsaicin with that 2.5 ppm of internal standard that was added. First, I'm going to look at the capsaicin peak. If I were to separate this chromatograph into 3 parts, starting here is our capsaicin, which has a mass to charge range around at 3.6. And this is due to the protonated version of the capsaicin having a peak here at 306.17. Something else to note on this spectrum is actually our internal standard that happens here, the protonated form at 294.14. All right, so next I'm going to look at the dihydrocapsaicin peak. It is at a mass range of 308, and that is because the protonated form on the mass spectrum is 308.14. All right, and finally, this is our internal standard peak, and as mentioned previously, this is based on its mass charge range at 294. All right, so this is our standards graphs that were prepared. As you can see here, we have our equation for capsaicin and dihydrocapsaicin. Something else to note too is you'll probably notice that our concentrations don't go very high, even though we prepared higher concentrations. This is due to the fact that our standards curves did actually start to level out based on just the abilities of our mass spec. So what we did is we lowered our range and based it on smaller concentrations, and we'll talk about how that affects our research a little bit later. So those equations from our standards graphs are then used to calculate the concentration of our sample. So here's the chromatograph for Frank's Red Hot Sauce. And as you can see here, this is our area, our peak area of each of our capsaicin, dihydrocapsaicin, and our internal standard. So in order to perform our calculations, we took the calculated concentration of each of our capsaicin, dihydrocapsaicin, and internal standard, and we were able to put this in our equation here, which as you can see is based on a wet determination. It is also to be noted that this number here is from a literature value stating that capsaicin in the wet form in ppm can be in a 16.1 to 1 ratio for SHU. So that goes back to the question that I asked at the beginning of my presentation, is how do those relate? So then this is our results for the red hot sauce. It was ran 3 times. And as you can see, there's still room for improvement because our dihydrocapsaicin is higher than our capsaicin, so we know that to be wrong. And also, as you can see, we calculated at around 28 SHU when the literature value for red should be around 450 SHU, which isn't only a 6% yield, so definitely a lot of room for improvement. All right, so I did mention an internal standard for extraction being N-vanillylnonamide. What is the value of adding an internal standard? And this is for extraction efficiency. And although this helps a lot with the efficiency of extraction, there are also some disadvantages that it's going to cause in our method as well. One of them is the dilution dilemma when trying to reach that linear range for analysis, which I had mentioned previously. Since our standards graphs will only be in that 0 to 20 ppm range, we then have to take our samples and we have to dilute them down to be able to fit in that range. But since we originally put in our internal standard and the preparations, that's going to cause issues with the dilutions. So one solution that we would be able to work on would be adding the internal standard in a higher concentration before before the dilution, so that way it would be able to fit into that range as well. All right, so besides the issue of adding the internal standard to the extraction procedure, there are a couple other issues that would need to be solved before releasing this to our target markets. One of them would be reaching concentrations beyond 20 ppm if we wanted to increase the limits of our instrument. This way we'd be able to offer testing for everything from low ppA or SHU being your bell peppers to pure capsaicin being peppers like the Carolina Reaper. And this would also be able to create easier preparation because we wouldn't have to dilute the samples. But it is also a solution to be able to do the dilution factors as well. Also, something to consider would be factoring water percentages of samples. Although it is common practice for analytical chemists to measure dry chemicals, that's not exactly how the consumer is going to perceive those kind of calculations because peppers are actually a wet mass. And also the Scoville heat unit is also, the Scoville heat unit scale is also based on the wet weight of peppers. So this does affect the dilution within the production of the, this does affect the dilution of the capsaicin in the plants. So extracting peppers in polar solvents as well is also going to, extracting peppers in polar solvents has the ability to extract water as well, so that's also going to be another dilution factor to take into consideration. So this is also another reason why we decided to pick salting out as an extraction solution. All right, so finally, I'm going to end off with a couple of potentials for future research. So I've already talked about 3 different markets, being novelty markets, production markets, as well as sauce manufacturing markets. But another one I'm going to talk about is the medical field, as well as the environmental field. So medical researchers are actually starting to find links between capsaicin and its beneficial role in fighting obesity, cardiovascular and gastrointestinal conditions, neurogenetic bladder conditions, various cancers, and even dermatological conditions. But one of the most common medicinal uses for capsaicin is for pain relief. And thinking back to talking about the TRPV1 receptors, since a TRPV1 receptor is part of the TRP ion channel, which helps regulate the body's sense of warmth, capsaicin actually has the ability to trick the brain into thinking that the body has a heating pack on any of the areas where capsaicin is applied. So this can even help with neurological pain, such as rheumatoid arthritis, diabetic nerve pain, and even HIV-related pain. So there's a lot of potential for medical research with capsaicin here. Next, looking at some of the environmental benefits, its most beneficial use is as an ecopesticide. And thinking back to the very first slide, relating the oleoresin in the capsicum genus as an effective pesticide or antifungal, but it also is very useful in keeping pests away. In 2012, an article did make the claim that capsaicin for crop production is going to be the next big advancement in agriculture. Even though this is yet to be proven, capsaicin has shown to be an effective biopesticide. And this again is due to the oleoresin present in the chemical, but it is also effective at keeping pests, insects, and rodents away from the plants. So this hasn't been used yet on a global scale, but the potential for this is limitless. All right, so here are my references. All right, so I'd like to take a second and thank the University of Wisconsin-Oshkosh Chemistry Department for getting me to this point. Wouldn't have been able to give this talk if I didn't know a lot of the chemistry that I did. And also for Dr. Crawford for putting up with me for all these years. All right, do we have any questions?
How much capsaicin do you have to spread on plants to get bugs not to eat them?
That is actually a really good question. I would imagine a bell pepper is not going to do much since it has very little capsaicin. I would base it on humans detection. So if you think it's spicy and you wouldn't want to eat it, I would relate that to other mammals since we have similar TRPV1 receptors.
So the next question is, why would I want spicy tomatoes?
Oh, spicy tomatoes.
Or spicy corn? Or
I wouldn't. I would recommend washing your fruits and vegetables before eating them.
Do you have any ideas on how to increase the range of your standard curve method?
There are a couple ideas, but the issue for this is by ionizing all of those molecules in the mass spec, it's going to create just a lot of stress on the machine. So even though there would be solutions for that, it might just be easier to lower our limit range into the linear range.
So that follows on, I think it follows on her question a little bit. You're using electrospray ionization.
Mm-hmm.
Can you explain how that works and why having too many ions might cause it to become very nonlinear.
Yes. So kind of how electrospray ionization works is it basically sprays your sample, and as that's being done, different charges are being put on that, and it's activating or ionizing each of your molecules. And if you get into higher concentrations, it's just hard to ionize everything. So it's just kind of difficult to be able to perform.
Draw a sketch of what's going on in the
Draw a
electrospray
sketch?
mass,
Oh my
electrospray.
gosh, I can try. Dr. Crawford's gonna be really disappointed in this. All right, so basically what we have is our sample is going to be shot out here, sprayed out, and as different charges are being put on, they are being potent. And so each of these molecules is then going to turn into a positive ion. So if you're spraying things in with higher concentrations, there's more things that need to be ionized. So then it just becomes very difficult. Very bad.
Actually asking for, where does the charge come from?
The charge
Do you have
comes from lasers.
an electron filament? Do you, what's going on?
Lasers. No, not lasers. I'm not quite sure. Any questions?
So I'm not sure, but in your reading, I was curious about the TRPV1 channel.
Mm-hmm.
So humans, we don't make capsaicin, and obviously in our bodies, but you said the TRPV1 receptor normally senses heat.
Mm-hmm.
So how does that work that with a small molecule binding to it and helping open the channel versus heat, or are there small molecules that the TRPV1 channel responds to that are normally made in the human body? I mean, sort of you have this compound from plants kind of co-opting the
Yes.
channel, so what does it do?
So are you kind of asking about like the activation and?
Right, yeah, are there other compounds that we make that activate that? Or
Yeah,
because heat is a
so
very different type of signal than an actual molecule binding.
yeah, so what kind of happens is the best way I can describe this is when you're talking about all of those receptors on your tongue, as you're eating a pepper, those capsaicin molecules will actually bind until something that can come in and dilute them, such as fats or oils, can take those off. So there are other things that can trigger those channels, but that's kind of how the activation occurs. I don't know if that answers your question.
Kind of, I guess it's probably a really hard question, but so heat is not a chemical usually, so
Yeah.
I'm interested, and we don't make capsaicin, so are there other, I don't know if you read anything about other compounds that we make outside of the tongue? Are these receptors found elsewhere in our body as well? So you mentioned neurological problems.
Yeah, I'm not entirely sure how they react to heat or like actual physical pain, but I do know that like such as the toxin, that's not like a capsaicinoid. That's actually a different analogous type of chemical that can also trip that. So, I mean, I'm sure there are other chemicals that are going to activate it. Sorry.
Okay.
Yes.
This is an extension on that. You said it. How is this actually gated? What causes it to open up?
That would. So when the capsaicin comes into the hydrophobic pockets,
Yeah,
or
you said you call it a specific gated type of channel.
a sodium ion ligand gated channel,
I thought you said that it was voltage gated.
a voltage gated. Yeah. So basically,
then
what happens is your neurons come in and they touch the dendrites of the cell, and thus all the neurotransmitters are going to come in and attach to your synaptic receptors, and that creates a chemical signal that gets transferred into an electrical signal, triggering an action potential, thus flowing neurotransmitters through the rest of your body. Is that kind of
And
answering?
So that causes it to open, right?
Yes.
So then, are these things like the toxin and the capsaicin, are they binding to other sites other than sort of what we typically gate this? I mean, you look at your picture that you have.
Yeah. Is this what you're talking about?
Mm-hmm.
Okay.
So what's going on here? So what's the blue and what's
Sure. Sorry. Any other questions?
If there are no other questions, let's thank Hannah.